few things I want to do, which I kind of skipped over as I was doing it last time because I didn't want to spend too much time on this. And none of you asked me questions about it, which was kind of nice. So I told you that the centripetal acceleration AC, right, is v squared over r, where you essentially have a circular motion taking place. This is uniform circular motion. So a particle, let's say, is going around in a circular track. This is the center, and the radius is r. And it's uniform circular motion. That means it has a fixed speed. And that fixed speed is v, right? So, and we talked about the fact that this is accelerated motion because of the way it works. So let's say I draw, it here. Okay. Suppose I draw a tangent here. This would be the vector velocity at this point, right? And this velocity vector is changing. Now suppose I take a point that is very, very close to it, okay? And I do the very same thing. It's hard to draw this, but I do the very same thing. So in other words, this is almost the same. So if I now want to take the difference between the final velocity, which would be the velocity at this point, let's call it point F final, and at this point, which was the initial point, then you can immediately see that the final velocity, I've just taken this vector and, well, I didn't draw it quite the way I should be drawing. So let me draw it better. Since I had it curved up. So let's say this is the final velocity, right? I've just taken this vector and put it here. And the initial velocity, as long as the two instants are really, really close, would pretty much be exactly opposite. Which means if there is a slight difference, that difference would be this way. So the idea is that V final and V initial, so if I do V final, this is minus V initial, I'm sorry. This gives you delta V, which is a slight difference in the velocity vector that has taken place between these two instants as you go from I to F. So it turns out that the way to get this is, actually this triangle is very difficult to draw, but I can imagine that if this is the radius of the circle, so if I draw a triangle here, and if I draw a triangle here, what you will see is that this is R, and this little length here would be an arc delta S. This, of course, is an extreme drawing. The more realistic drawing would be V final here, okay, and then V initial. So V initial. This is minus V initial. V initial would be this way, so plus V initial, and this would be my delta V. So this is just to give you an example that these are, when you do V final minus V initial, it's almost like you're adding two vectors which are equal and opposite. But the actual triangle, if I drew the triangle with the vectors, the sliver would look like this. This is the V initial, and this is the V final. I can put in colors, maybe that will help. So let's say this is the V final, and this one is the V initial. This is the V final. Why am I telling you this? I'm telling you this because this triangle here, comprising of the vectors, and this triangle here, which is just this triangle here, this triangle. This triangle pertains to the triangle associated with the vectors here. These two triangles are similar triangles. They have the exact same properties. And the properties basically are that these two are very close, and this is almost at 90 degrees. Of course, it can't be 90 degrees, but it's very close to it. So one therefore can write delta V over V, the magnitude, is equal to delta S. This is delta S over R. So this is the trick. It's an important trick, but it's a trick. So the trick is basically saying that the triangle with the vectors is similar to, congruent to, the triangle with R and delta S. Why should that be the case? But it's very simple, because you see, this line and this line are at 90 degrees. This line and the other line is at 90 degrees. And actually this delta V hence becomes identical to delta S if you take the ratio. So therefore, this relationship must be valid. If this relationship is valid, then I can write this as delta V equals V delta S over R. Okay? But I can also write then centripetal acceleration as delta V over delta T. By definition, acceleration is the time rate in which velocity would change. So therefore, AC would be delta V over delta T. So in other words, if I put a delta T here, I better put a delta T here as well to make the equations work. So that makes it very pretty, because delta S over delta T is nothing but V. So it will become V delta S over delta T divided by R. But this also is a V, and that's the reason why we have centripetal acceleration as V squared over R. So I just wanted you to understand where this formula came from. There is a simple way of understanding it using vectors, triangles, and congruent triangles. As long as you remember a little bit of geometry and you realize that this triangle here, which I have drawn here, and this triangle here are identical, but just turned around by 90 degrees, that is more than sufficient for you to do the rest of the work. That is more than sufficient for you to reach this starting point. And once you reach this starting point, you can basically immediately see where this thing is. Any questions? Okay. I will talk more about centripetal forces as we go along, but let me first get on with some other things which I think is quite important. So we started doing these free body or force diagrams. Different people call them differently. One can call it a force diagram, and interchangeably they are used. One can also call it a free body diagram. Okay. So a free body diagram is essentially a diagram in which you are laying out the forces acting on object or objects that you are looking at. So we did a bit of that. So suppose you have a block, like I have in the homework. I put a book. A book can be a block, which is sitting on some surface. So whenever you have something sitting on a surface, this thing has a mass. So therefore, there is a downward force, which would be mg. This is I can put a vector here, but let's do it for now. And by Newton's third law, which basically says that action is always accompanied by some kind of a reaction force, then you should have some kind of a force like this, which would be your surface force. Okay? So that's part of the story. That's the vertical part of the story. Now suppose nothing else is being done, you are done at this point. If it's not being pushed or pulled in the horizontal direction, this is the end of the story. But suppose you decide to pull it that way. Now that can be a pull by attaching a string, that can be a push from here, but suppose there is a force that way, on the right side. Let's call this force F. This should have an arrow, because we are putting an arrow. So if this force is F, then two things can happen. A, you may not have any frictional force at all. So for example, you can be on a surface that's very smooth like ice, in which case you don't have any frictional force. In which case this F will immediately give you an accelerating block, because Newton's second law tells us that F is mass times acceleration. So if there is no opposing force, you are done. F is equal to ma as far as the horizontal direction is concerned. And as far as the vertical direction is concerned, these two are opposing each other in such a way that Fs going upward minus mg must be equal to 0, because there is no net force in the vertical direction. So that's my force equation for this. Now if there is no friction, then I can write F is mass times acceleration. Right? Acceleration A pertains to acceleration of my block here. But suppose there is friction. It's always a good idea to write this like this. This is the y equation and this is the x equation. Just so that you know that you have taken care of the x and the y pieces diligently, because you need both to do these problems. So suppose there is friction. We always know that friction is an opposing force. By the way, friction is a very tricky force. I'll tell you a little bit about friction today. But for now, let's do it operationally. So if there is a force that way, that means there would be a friction that will be opposing the motion. Friction never helps you. Friction is always going to hurt you. So if you ever find that friction is actually increasing your acceleration in the direction in which you're applying the force, be assured that you made a mistake. All right? That's the easiest way to make sure that you have miscalculated something as far as friction is concerned. So friction will always be an opposing force, and let me write friction as F friction. So therefore I would say that my rightward force is F minus F friction must be equal to ma. All right? So that is the case for the horizontal motion. This is the case when there is friction. All right, now two things can happen. So in this case, as you can see, that there is a difference such that you have an ma, and this ma is your net force. That's your net force. If there is a net force, there will always be an acceleration. If there is a net force, there will always be an acceleration. So if I tell you that something is moving at uniform velocity and there is friction, that necessarily means acceleration is 0, because I told you it's moving at uniform velocity. So if acceleration is 0, as far as you are concerned, that means the forces are in equilibrium, even though the thing is moving. So moving at fixed velocity leaves you with the exact same predicament had the right hand side by 0, had the right hand side replaced by 0. So uniform velocity motion, of course uniform velocity can be 0 also. With friction actually gives you F minus F friction equal to 0. So there is no net force. No net force because it is moving at uniform velocity and your acceleration is 0. These are very tricky things, and if you are not paying a great deal of careful attention here, you will miss this, because just like I told you a long time ago, that if I drop something, that's a technical word. Dropping means the initial velocity is 0. This is exactly the same. If I say that there is uniform velocity motion and there are forces acting, that's also a technical word. And there is a very clear meaning. And the meaning is there is no net force. You cannot have a net force. No matter how many forces that act on it, at the end of the day, the right-hand side of the equation should be 0. There is no net force. All right. So let me now tell you a little bit about this friction force. I'll just take a detour, and then I'll come back to constructing more of these force diagrams. So what is this friction force? Well, the friction force is a force that's arising because you're trying to move something on a surface that can really not be smooth. There is no such, just like there is no place in the universe where there is no force acting on you. There is no place where there is no friction. Just about. Every place, every event that you examine, you'll find that there are some opposing forces somehow. So there is some amount of frictional resistance, whether you call it friction, whether you call it viscosity, whether you call it air drag, there is some equivalent of that. They're not all the same, which is what makes friction a complex beast, because friction depends upon the surface and so on and so forth. So the thing that you need to know, though, operationally for now, let's take a very simple thing. Let's take this block that we have, and let's say you want to push this block. So you're applying a certain force on this block, and suppose the block is sufficiently massive and the surface on which the block rests is sufficiently rough from experience such that this block is not so easy to push. Suppose you are pushing, to give you a concrete example, a piece of furniture on a carpet. We all know that's not the easiest thing to do because the carpet's never happy about it. So it turns out now that this ground will obviously give you a friction force. And if you could, so I'll never succeed in pushing this table because it is anchored to the ground, but let me just, so if I were to push it and nothing happens, I'm still putting the force in, but it's not going anywhere. So that means the force I'm putting in is therefore less than the resistance force that this table can offer. Let's say this table is movable in no time. So there will be a regime where this force will be such that the friction force will be able to negate this force. It can't push you back. It can't do that because this force arises because of that force. So it can, however, ramp itself up as you raise your force such that you still are not able to move. But this can't go on forever, right? So it depends upon the surface. But it turns out that if you, let me make sure I can make a nice drawing of this. I actually don't have a nice drawing of it. Anyway, the books do. But the idea basically is that as you apply this force, as you increase the amount of force you have applied, the friction force counters you. And as you increase the force, the friction force keeps increasing. Okay? Nothing happens, no motion. Friction force just counters you. You push harder, this one gives you an equally harder resistance force. But ultimately there is a breaking point that you'll reach. Okay? So what happens here is that this friction force can no longer counter the F that you're going to give it. So what happens is that it actually goes down a little bit and becomes stable. All right? So what happens is that the friction force therefore has two regimes. This is a static regime here, and this is a kinetic. Kinetic means motion, as you saw before, and this therefore is the kinetic regime. So friction force has two regimes. So therefore friction is very complicated. We have been using friction already, but we are not going to get into the depths of friction. By the way, friction is a living, thriving area of research in physics, in mechanical engineering, in nanoscale studies, which is called tribology. It's a very important area of research, partly because we have to deal with friction and we pay for friction, right? I mean, while friction is helpful, I mean, just because my shoes have a rubber sole, I'm not falling here. So it's helpful, but friction also is a reason why we actually have to expend a lot more energy to overcome it than otherwise. So friction is a double-edged sword. More often than not, we are paying for friction. By the way, there was a study done by Exxon, I think, in which they pointed out that 1/3 of America's GDP, so 1/3 of America's income, is spent on overcoming dissipative forces. And dissipative forces, friction is one of them. Okay? There are many other dissipative forces, electrical resistance, so on and so forth. But overcoming natural resistance to processes costs you 1/3 of the income that you'll ever make in your life. So let's say you earn $3 million in your life, which is a lot of money, I think. Well, say goodbye to 1 million for friction. So friction is a big deal, you better know about it. So this is a kinetic friction, this is the static friction. The way friction works is that we write a friction in a certain way, and this formula is very important. Basically, we have already seen a friction is proportional to the force that is applied. We have already seen that. So whenever you have a proportionality like that, then typically what it means is that you can write a friction is some constant times the force. So this constant is called the coefficient of friction. And it is typically denoted by the symbol mu. So if I give you the symbol mu, mu, that is always used for friction. So scientists are very fastidious about symbols used. For example, we use small t for time, which I taught you a long time back. We use small x for x displacement, small y for y displacement. We use small g for gravity. You don't use big G for gravity. Big G is reserved for somebody else. So we are very fastidious about it. Mu is the coefficient of friction, just like that. It's a very specific quantity, very specific symbol that's used. And there are two kinds of mu. So up until this point in the static regime, you have static friction. On the other side, you have kinetic friction. So static friction is denoted by mu s. A lot of times you yourself have to determine if you're going to use static friction or kinetic friction. Right now I'm giving you, but this will change. Whereas when the thing is moving, you are going to deal with kinetic friction. Okay. So you see, in this part, you will actually have mu k coming into play on this side, right? And on the shaded side here, you'll have mu s coming into play. So mu s is not fixed, because more force you apply, more friction force the thing gives you until it reaches a breaking point. So it has a maximum. So therefore, this is the maximum friction force, and we normally would typically deal with this point as the point of interest with regard to static friction, because there it reaches a unique value. So when I give you the mu s, by default I'm talking about mu s at this point when it reaches the maximum value. In fact, I might even use the word that the maximum value of static friction, mu s, is equal to da da da. That's what I'm talking about. Okay? So what I'm trying to tell you, the reason why I went through all this business is because, let's go back to this problem here, and you look at a friction, and then you immediately see, aha, I have a friction here, and I know that a friction is, actually I made a statement here that is not correct. This force here is actually the normal force, so, or the surface force. So while this force is ramping up with friction, but friction force itself has something to do with mg and the surface force. So this is mg and this is Fs. So this is actually proportional to Fs. So let's just correct it and put Fs here. And this is actually the applied force, but this part is Fs. Okay? So it turns out then that F friction is some coefficient of friction, mu s or k, times Fs, surface force. But you see, if you look here, the surface force is mg. So therefore, what you are left with is that is mu s or k, in this case anyway, mg. But I would caution you that this is a special case. I'll tell you why in a moment. This is a special case. So in other words, if I go back to this problem, then I should be able to write the first equation, the y equation, as Fs minus Ma equal to mg equal to 0. The x equation would be applied force F minus friction force. So friction force itself, depending upon whether the block is actually stuck or moving, S or K, I leave it to you to take a decision, times Fs. And this must be equal to 0 or mg as the case, Ma as the case may be in general. Any questions so far? Okay. Now, the reason why I gave this proviso is because the normal force is not always mg, right? Because think about it. If the block is sitting on a flat surface, then of course I have mg, and the normal force, which is normal to the surface, will be exactly opposite and upward. So clearly, for you to have equilibrium, here your Fs is mg. But suppose that's not the case. Suppose I have an inclined surface. In an inclined surface, I'll have a block here, right? But we have already talked about the fact that mg is vertically downward. Right? Mg is vertically downward. Guys, if you can't see, just come closer. Mg is vertically downward. So therefore the normal force must be that way, right? So here Fs is not equal to mg. How do you figure out what it is? Well, let me get to that. Because of our snow days, this class is proceeding at a rate which is slightly different from my last year's lectures, which are on YouTube. So in terms of YouTube lectures, I'm in lecture 10, I think. Okay, just so that you know where I am. So let us broaden this problem to that on an inclined plane, just like I tried to draw there. So here you have a block, let's say, okay? And let's analyze the forces on this block. And I tell you ahead of time that this incline makes some angle, let's say alpha, with respect to the horizontal. So this is the horizontal, makes some angle alpha. So this is a typical case of, you're putting heavy furniture onto a truck, taking it down, putting your lawnmower in your car, you put a ramp, you're in a wheelchair, you end up on a ramp if you're going downstairs, down a level. So anyway, so mg is like that. Mg will always be vertically downward because It's the center of the earth that's pulling you, right? There's no choice. As I already told you, the normal force would be that way, surface force. So in this system, you don't set your x and y as horizontal and vertical. Okay, it's very important. A lot of students tend to have trouble here, so I'm warning you ahead of time. When you have an inclined plane, it is not convenient for us to use x and y as horizontal and vertical anymore. You see, I can make my x and y any direction I want for convenience. It's a convenience thing. So you've got to be smart about it. So what we'll do is we'll say, okay, fine. So this is the direction, this is the normal force to the surface. So I'm going to extend this line. So clearly, this line here is perpendicular to the incline, right? So the blue line is perpendicular to the incline, but at the same time, my mg line, let me call it the green line. Unfortunately, I don't have a fancy chalk today, which can make it look very different. All the colors are pretty boring colors for some reason. It won't help you anymore. So this green one, this is the mg one, on the other hand, is perpendicular to the horizontal surface. Why am I showing you this? The reason why I'm showing you this is because if I take my fingers and point it like this, and then if I turn my finger 90 degrees, isn't this the triangle you get? Right? So that means if this is alpha, this fellow must be alpha. So that's very important. So many people make a mistake here. But as long as you realize what you really have done is you have actually taken this angle and over here you turn it around by 90 degrees, you can't go wrong. It's as simple as it can be. Why is this important? I'll tell you why it's important. Because you see, you can now write an equation along this line, because you can say that I have Fs upward minus mg cosine of alpha, and that must be 0. So that now becomes your new y equation, and this now becomes your new y-axis. This is why I was telling you we can change our axes any way we want for our own convenience. So you see, that means my x-axis got to be that way. So this is going to be my x-axis. If that's y, I can call this x. So you see, if this is mg, and this piece obviously, because this is alpha, adjacent, so this is going to be your mg cosine of alpha. That means there will be a tendency for this block to go downward, because there will be a force here along the incline, along the x-axis, as a component of your mg. And that force along the x-axis now is going to be mg sine alpha. Okay? So clearly, if this is a block made out of any normal material, there will be a friction force. And if there's a friction force, the friction force will oppose it back. So therefore, I can call this my F friction. Right? So then I have mg sine alpha minus F friction. And if the friction force can't balance things out completely, I must allow for a net acceleration, net force resulting in net acceleration, which should be downward along the incline, because the friction force is an opposing force here. So it should be downward. So therefore, the picture I've drawn would be consistent in this case, not in all cases, with a downward acceleration. Okay. So now let's see what we can unearth about this friction force, because I've already told you that friction force is the coefficient of friction, static or kinetic as needed, times the normal force. So therefore my friction force I can write out as mu s. In this case, suppose there is motion, so mu k times Fs, and I already know from the first equation that will be mu k times mg cosine of alpha. Okay? So you see, this equation now, my x equation, with this condition, becomes mg sine of alpha minus, in this case there is a motion mu k, and Fs now becomes mg cosine of alpha, and this is equal to ma. Now if it turns out the thing is static and acceleration is 0, so if there is equilibrium and A is 0, A is 0 means either the velocity is 0 or the velocity is constant. Both cases are allowed by Newton's second law, right? Because zero acceleration just means zero acceleration. That means there can be finite velocity. So in that case, of course, this side would be 0 if there is equilibrium. If there is no equilibrium, that becomes your new x equation. So in all these problems, this is the deal that's going on. So let me now broaden it a little bit more while I am on the topic. And add one more piece to this puzzle. So the one more piece would be, suppose I have the inclined plane and suppose I have the block. So I know this is alpha, right? This is mg, right? So this is alpha means this is alpha, which means I have to draw axes like these. So this is Fs. First label out the forces before you forget, because chances are otherwise you'll make a mistake. So there'll be an mg cosine alpha that way and an mg sine alpha this way. So let me label it out so I don't forget. Mg cosine of alpha, and then you have mg sine of alpha here. Now there is a decision point, because I want to add something else to the problem. So what I want to add is I want to add a rope here, as if I am pulling upward along the incline with a tension T. So this would be a class of problems that you'll be doing for this course. So, and typically the free body diagram that you'll be worrying about for those problems would be like that. So there is an mg sine alpha down along the incline, and then there is a tension force as if something is pulling it up. There could be a pulley here or something. These are all practical engineering cases, so there's nothing odd about them. There are many, many machines that are built with these properties. That's why we do that. But then you see, depending upon whether it's going down or going up, the direction of friction will have to be set. Because remember, friction is always opposing you. So if tension force is winning and it's actually being pulled up, friction will be downward. On the other hand, if tension force is not strong enough and mg sine alpha makes it go down, friction will be upward. So this is a problem, therefore, that is very tricky. And you are the person who will be making the call as to which direction friction force would be. So in this case, let me assume that the motion is upward, meaning that way, which means friction force must be this way. I could have done the exact opposite thing, but I'm just doing this. So now you see what happens is that as far as the x as far as the y-axis is concerned, this is my y-axis. Again, I have this exact same thing. I have fs minus mg cosine of alpha is equal to 0. But the x-axis motion, which is along the incline motion, is going to be far more complicated. So x-axis motion, I have already told you that t is the winning force. So I will put t first and make the direction of t to be positive. From that I'll subtract off mg sine alpha, which is the downward force due to gravity, due to mg, that's along the incline. And then I have a friction force, so I'd write it in 2 steps, F friction, then I will give F friction the right stuff it needs, and this would now determine the net acceleration ma. Now, even if the thing is stuck, but it has a tendency to go upward if it could, then friction would still be opposing. And that would be a case where ma can be 0, but you can still have opposing friction, because if it could, it would tend to go upward. If on the other hand it would tend to go downward, then you have to take the sum. So these problems are very delicate, okay? So that's what I want to say. Let's not get ahead of us. Let's first set this up. So now we already know that F friction, by definition, in this case there is motion, let's say, is going to be mu k times Fs. And from equation for the y, I already know that this will be mu k times mg cosine of alpha. So therefore my x equation with this condition now becomes t minus mg sine alpha minus mu k mg cosine alpha is equal to ma. Doesn't look totally simple and pretty, and it's not. But this is the next thing that you are doing. Okay? So it's setting up these equations that are now becoming the next challenge for you. So I'm going to do something now because that's very important. And it's also kind of basic. We are going to ride on an elevator. Not in an actual elevator, but in an imagined elevator. I'm sorry. I wish I could take you and put you on the Fronzak elevator, but I can assure you that won't be pleasant because it will break. So the issue about the elevator has to do with the issue of weight. Now weight is a very, very tricky thing. Why is weight a tricky thing? Because weight depends upon how and where it's measured. We already know that we are weightless in space, almost. So that doesn't mean something special happens to you. Well, it does, but apparently if you just go to space, your mass remains the same, but your weight goes away. So there is a difference between our mass, that is how much matter we are made of, and the weight itself, which is that mass times some acceleration. When we are on Earth, that is typically acceleration to gravity. But is it? That's the question. So suppose you wake up in the morning pretty grumpy and sleepy, and you put yourself on the weighing scale. And then you figure out your weight. The weight you figure out is because you're pushing down on the weighing scale, and the weighing scale is giving you a normal force back. So therefore, in this case, you're presumably in equilibrium. So Fs minus mg is equal to 0, and therefore Fs is equal to mg. So in this case, although we would colloquially say that my weight is mg, that is actually not correct. Your weight is Fs, because Fs is what is giving you the counter force. And it is a counter force that has to do with our weight. So when we are in space, there is nothing that stops you from standing on a weighing scale if you could. Somehow hold things well and stand there. That wouldn't give you your mg. That would just give you basically almost nothing, because you'll hardly be able to touch the surface. And unless you jump on it, it won't give you an Fs, which is a non-zero reading pretty much. So you see, the weight is this guy. Not the other guy. That's the weight. All right. So now suppose you become very creative and you take your bathroom scale everywhere, and including your elevator. So now suppose this is your elevator, and here you are on the bathroom scale in the elevator. Nothing wrong with that, you can do that. And again we do the same thing. You have mg downward, elevator gives you a surface force Fs, weighing scale gives you a surface force Fs. But now because you're in an elevator, you have the privilege of going up or down. And once you want to go up or down, since the elevator was at rest, it's got to accelerate up or down. So let's say you start off in the elevator and say first time you want to go up. So tell me something. If you step on an elevator and the elevator starts to go up, how do you feel? Yeah. Heavier, right? Anybody feels lighter when the elevator starts to go up? All right. So then we all agree, or mostly agree, that if the elevator starts going upward with an acceleration a, you should feel heavier. So let's set up the force equations for this guy, because we actually have drawn a free body diagram already, right? So now since the upward thing wins, I would write Fs upward minus mg, and the net force is ma upward. Be very careful, because there is a 100% chance of making a mistake in setting up the equation. So mark my words that I set up the equation with the winning force, ultimate winning force taken as the positive. Ultimate winning force was the elevator going up. So A must be up. So if A is up, so first I determined A is up. That's what we discussed. If A is up, then on the left side, I first put Fs, which is up, minus mg, and then equal to ma. So this is very important, because unless, no friction yet. Fs is the surface force, just from the ma is the force that you feel by being in an accelerating elevator. So if the elevator is accelerating with A, since you are in the elevator, you will also be accelerating with A, right? So therefore the net force you will feel, because your mass is m, would be ma.
Is there such thing as a friction bond?
Yeah, but we don't worry about that here, because that has to do with the entire elevator itself. It doesn't affect us. Any other questions? Okay, so now see what happens. Remember I told you Fs is your weight, although you are skeptical. So now you see Fs is actually going to be m times g plus a if I take the mg to the other side. So if the acceleration of the elevator is 1 meter per second squared, it's g, which is 9.8 plus 1 meter per second squared, 10.8 meter per second squared. That will be multiplied with your mass to get you your effective weight. That is the reason why you feel heavier. So isn't that cool? If you want to increase your weight, just get on an elevator and accelerate. Now you see, I can tell you a wonderful way of reducing your weight. Since America is obsessed with the disease of having to reduce weight, I'll tell you a beautiful way of doing that. And you can pay me for it later. People are making millions of bucks, why shouldn't I get some money for it? So all you do is that you get back on the elevator, put your scale down, here you are, Again you have mg downward. Again you have fs upward. But now instead of pressing the up button, you press the down button. Bingo. There you go. Now the acceleration would be downward. So now you see what happens is that this is downward. So I would write the winning force is mg minus fs is equal to ma. So now what will happen is fs, if I take it to the other side, is going to be mg minus ma, and you would have lost your weight now. M times g minus a. In fact, this is so powerful that if you are on free fall, so free fall, which implies that you're falling with acceleration g, your fs will become precisely equal to 0. So I've also told you how to become completely weightless. So this is the prelude to doing pulleys. So what we'll do next is we'll put masses on pulleys, on a pulley disk actually, and solve that problem, and then we'll link this problem, the inclined plane and the pulley, back up. That we'll do after the exam.